Okay guys, this is going to be a video, a real quick one on electrophilic substitution mechanisms, alright? And this is under the Aromatic Chemistry topic, which is on the advanced spec for paper 2, so check it out right here. This is from an AQA past paper, paper 2 June 2017, so check it out if you want. I'm going to jump straight into this, okay? Nitrobenzenes is what this question is about. Nitrobenzene reacts when heated with a mixture of concentrated nitric acid and concentrated sulfuric acid to form a mixture of 3 isometric dinitrobenzene. Write an equation for the reaction of conc HNO3 with conc H2SO4 to form the species that reacts with nitrobenzene. So within this topic, okay, this is nitration of benzene topic. Even though we're starting as a nitrobenzene, it's still a nitration, okay, because ultimately all we're doing is adding on another nitrate group, okay, and the nitrate happens to be our electrophile. So we have to write an equation to show the formation of the electrophile, okay, and that is our species right here. So for this topic, okay, for both the Friedel-Crafts acylation and the nitration, you need to know the equation for the formation of the electrophile, as well as the equations of how the catalyst acts, how the catalyst acts as a catalyst. I don't know how else to say it, but you get what I mean. So those ones are two-stage reactions, and this one is a single reaction, okay? So within this equation, we're going to have our conc HNO3, so I'm just going to put that in right here, HNO3. Like I said, flashcards are your best friend. Now, this reacts with sulfuric acid, okay? So I just remember this off the top of my head. There's 2 moles of this guy, 2H2SO4. This is going to produce us 2HSO4 minus plus our electrophile, okay? NO2 plus our hydronium ion, okay? So within this reaction, this H2SO4 is the catalyst, okay? So if you wanted to write out the second step of the equation to show the regeneration of the catalyst, it's just going to be our HSO4 minus, this guy right here, plus a H plus, and that's just going to reform our H2SO4. Okay, now, where does this H plus come from? I'm going to get into that in a second, okay? So name of the mechanism, sort of given this away already, but this is an electrophilic substitution. Okay, you want to write out the full thing, but I'm just shortening it down for this video. So what happens here? I'm going to start with our nitrobenzene, okay? Now, they haven't told us the position of the initial reactant, but they have told us that it has to be separated by 1 carbon. So there's 1 carbon in between them because it's 1,3-dinitrobenzene. So ultimately, wherever we start the reactant, we have to finish it to make sure it makes sense. I'm probably butchering this explanation, but hopefully you get the idea. So this right here, okay, let's say that I'm just going to start it right here. Okay, by convention, this is the 1 position of the aromatics, but obviously you can just spin this round as much as you want to make any of the carbons 1. Hopefully that makes sense. So I'm just going to start it up here, okay? Now, what we're going to do is we're going to take our electrophile, the NO2 plus, okay? All electrophiles are electron pair acceptors. That's the definition you need to know for AQA, okay? So NO2 plus, ultimately, I'm actually going to switch this up because AQA can be a nightmare sometimes. The plus has to be on the nitrogen, okay? That's essentially what's happening here. Now, I'm going to change my color up to a nice blue. What happens is we have this ring right here, this fat ring, okay? This is our region of electron density, our delocalized electron ring. So what happens is you have to draw a curly arrow from the point of the ring, anywhere on the ring essentially, ideally on the right-hand side here, it's going to go onto our NO2 plus, okay? Incredibly electron dense, okay? Negative is going to be attracted to this positive, opposite charges attract. Pretty simple there, okay? So what we have to do is show the formation of our intermediate, and that's what I'm going to do right here. So remember I said that we have to make sure that our final product matches 1,3-dinitrobenzene. So if our first one is here, NO2, and I'm going to call that our first position right here, our first carbon, the other one ultimately has to go here. Because if it was here, it's going to be 1,2-dinitrobenzene, which it can't be. So I'm going to write it here, okay? So that's going to be NO2. And then we've also got a H here, okay? A hydrogen right here. And that's because within the skeletal formula, all of these carbons on the corners are attached to 1 hydrogen each, okay? Apart from this guy right here. So this is our intermediate right here. And what we have to show next is the ring, okay? Now, when this ring donates a lone pair onto the electrophile in order to form this covalent bond right here, it actually breaks open, okay? So we have to show that. So I'm going to show that right here, just by this structure here, which is known as a horseshoe, okay? And due to it it lost electrons, therefore it essentially gains positivity, okay? One thing you need to keep in mind within AQA is that they do not like the horseshoe to cross the adjacent carbon boundaries of where the electrophile joined. Okay, so this red circle is the carbon that the electrophile bonded to. They do not like to see this horseshoe cross the boundaries of the adjacent carbon. Okay, so just keep that in mind. Let me back up here for a second. Now this hydrogen is obviously now going to have to donate its bonding pair in this covalent bond back onto the ring to restore the stability and the charge. So this goes in there like that, okay? Now, when we're showing these curly arrows, you always want to show the curly arrow either going from the center of the bond onto something. Like, it doesn't have to be the center, it can be anywhere along the bond. Or from a lone pair onto something else to form a bond, okay? That's all organic mechanisms are, okay? The breaking and formation of covalent bonds. I don't know why they don't teach it like that, but that's literally as simple as it gets, okay? So what I'm going to do here is just show our final product, our 1,3-dinitrobenzene. So if we draw this out, our electron dense ring has reformed here. We're going to have our NO2, and we're going to have our NO2 at the 3 and the 1 position, okay? And that's all our marks right there. So 1 mark right there, and then how do our marks add up here, okay? So we've got 1 mark for this curly arrow. We're going to get 1 mark for this curly arrow here. Going to get 1 mark for the horseshoe and the structure and the charge and all that good stuff. And then ultimately, our first mark is going to come from the name itself. 5 marks right there. Hopefully that was helpful, okay? These mechanisms aren't hard. Exactly the same mechanism as the Friedel-Crafts acylation mechanism you need to know. But yeah, just keep practicing, keep going with those past papers. I really hope this was helpful. If you learned something, be sure to like the video, subscribe for future maths and science content. Best of luck in your upcoming exams. Peace.